Most LLM agents behave almost the same, no matter what you call them or how you describe their role. You might give one agent the title researcher and another the title analyst, but when you actually test them, the outputs, the reasoning patterns, and even the failure cases look nearly identical. Why does this happen? Because role descriptions alone don't meaningfully constrain the model. The system prompt may sound specific, but the model still has the full freedom to reason however it wants. In this video, we are going to look at the reason why agents behave generically and, more importantly, what you can do about it. I will show you the structural elements that actually shape behavior, things like constraints, cognitive boundaries, and decomposition strategies, and how you can engineer them intentionally. Once you understand these ingredients, you will never rely on the role strings again. Most agent designs fail for the same group of reasons. The first problem is shallow roles. A role description like "you are a helpful assistant" or even "you are a senior strategist" has almost no effect on actual behavior. It's too abstract, too vague, and too easy for the model to ignore. The second problem is tasks that are far too broad. When you give an agent an open-ended objective, it has to improvise the entire reasoning process from scratch, which leads to unpredictable results. Next, most agents have no explicit boundaries. Nothing tells the model what not to do or where its cognitive limits should stop. Without boundaries, the model overreaches, overexplains, or hallucinates steps that shouldn't exist. And finally, almost no one includes failure mode planning. That means the agent has no way to recognize when it's outside its expertise or when it should stop, ask for clarification, or hand off the task. In short, broad tasks, shallow roles, missing boundaries, and no safety rails. This is why agents collapse into generic, unreliable behavior. A role is just a label. It doesn't create behavior by itself. Real behavior comes from structure, specifically from constraints, cognitive boundaries, and decomposition strategies. Think of the behavioral architecture like a three-layer stack. At the very top is the role layer, but it's thin because it contributes the least to real behavior. It mainly sets context. Beneath that is the constraint layer. This is where you actively limit what the agent is allowed to do. Constraints shape decision making far more than abstract role instructions. At the bottom is the cognitive boundary layer, the thickest and most important layer. This defines the agent's thinking limits, the scope of its reasoning, and the mental territory it is allowed to operate in. When these layers work together, you get reliable, repeatable behavior. If you rely only on the role layer, you get generic output. This is the core concept for the rest of the video. Behavior is engineered through boundaries and constraints, and not through titles or personality descriptions. To architect consistent agent behavior, you wrap the agent in what I call a behavior shell. The behavior shell sits directly between the input and the LLM. Its job is to shape the task before the model ever sees it, and to enforce how the model is allowed to respond. The shell has 5 major components. First, input shaping. You take the role task and transform it into a structured version that aligns with the agent's responsibilities. Second, reasoning limits. You explicitly set how deep the agent can think, how many steps it can take, and how broad its reasoning scope may be. Third, allowed operations. This defines exactly what actions the agent is permitted to perform. Anything outside this list is off limits. Fourth, prohibited operations. These guardrails prevent the model from drifting into tasks it shouldn't handle, such as writing code when it's only supposed to analyze requirements. And finally, the output schema. This ensures the model's responses follow a predictable structure that downstream systems can depend on. When you combine these components, you turn a free-form language model into a controlled cognitive unit with a stable identity. This is the foundation of engineered specialization. Now let's translate the behavioral architecture into actual code. We will build 4 modular components, each responsible for one part of the behavioral shell. We start with behavior spec. This object defines the agent's persona, its high-level goal, and what operations it is allowed or forbidden from performing. Think of it as the structural blueprint for the agent's behavior. Next is cognitive boundaries. This component enforces how deeply the agent is allowed to think. By limiting reasoning steps, we prevent the model from wandering outside its expected domain. Then we have constraint prompts. This module injects explicit constraints, both required behaviors and forbidden behaviors, directly into the prompt. This is one of the most impactful parts of shaping behavior. Finally, output guard. This validates and enforces a strict responses format. If the model deviates, you catch the error early and maintain consistency. When these four components work in sequence, they create a predictable and controllable workflow that fits into the LLM. The output that comes out is no longer generic. It's specialized, stable, and aligned with the behavior you engineered. Let's begin by creating a brand new folder for the behavior agent project. I'll call it Agent Behavior Architecture. Once it's created, let's go into it. Next, let's create a dedicated Python virtual environment. This keeps our dependencies isolated and guarantees a clean setup. Now, let's activate the virtual environment. If you see venv in the beginning, that means your virtual environment is active. Now, let's create a new file, which we will call requirements.txt. Inside of this file, we will put the two dependencies that we need. The first one is the official OpenAI client library. We will use it to call the model. The second is Pydantic version 2. We will use it for a strict validation of the agent's output. Now let's install them. This command will install both dependencies now. It will take a few seconds. When you see an output like this means that everything was successfully installed. Now let's create the main architecture file called behavior.py. This is where we will define every part of the behavioral shell. At the top, I'm importing three things. Base model and validation error from Pydantic will give a strong schema validation. We will need list from the typing module for type annotations. And we will use JSON to safely load model outputs before validating them. Next, I'm defining a class called behavior_spec. This is the backbone of our behavioral shell. It describes what kind of agent we are creating and what rules it must obey. We have 5 fields: name, goal, allowed operations, which is a list of actions that the agent is permitted to perform, prohibited operations, which is a list of actions the agent must never perform, and reasoning depth. This is how deep the agent is allowed to think. This one object defines the entire behavioral identity of the agent. Now I'm creating a class called cognitive boundaries. This controls how deeply the agent is allowed to think. The constructor stores a single value called max steps. The apply method prepends a very explicit instruction to the prompt, telling the model exactly how many steps of reasoning it is allowed to use. This prevents the model from wandering or over-explaining. It gives us tighter, more predictable behavior. Now I'm adding the constraint prompt class. This component enforces the rules from the behavior spec. Inside the apply method, we take the allowed operations and prohibited operations and turn them into readable comma-separated lists. Then we construct a block of text that explicitly states who the agent is, what its goal is, what it is allowed to do, what it is forbidden to do. This is the lowest level control we have over the model's behavior. And finally, we create the output guard. This class enforces the exact schema the model must return. It must output a JSON object with a reasoning field and an answer field. No more and no less than that. The validate JSON method takes the raw string from the model, tries to parse it as JSON and validates it against this schema. If anything is wrong, missing fields, invalid JSON or unexpected structure, it raises a validation error. This guarantees structured, predictable outputs. Now we need to create a new file which will be used to store our OpenAI API key. Make sure to never commit this file to GitHub because it's sensitive. Next, let's create the main.py file. This file will contain the behavioral agent itself and the demo code. I'm importing the 4 components we just created. We also import JSON and we bring in the OpenAI client class. I'm initializing the OpenAI client. It automatically reads the API key from the environment. Now, I'm defining the behavioral agent class. The constructor takes the behavior spec and stores it. Then it creates a cognitive boundaries instance using the reasoning depth from the spec. This links the behavioral contract directly to the boundary mechanism. Next, the build prompt method assembles the final prompt. First we apply the constraints, and then we apply the cognitive boundaries. Next we prepend a system header that tells the agent exactly how to behave and that it must respond only in JSON. Then we include a schema hint showing the exact JSON format required. Finally, we return all of these pieces combined together. This is the full behavior shaped prompt. The run method actually calls the LLM. We turn the user input into a final shaped prompt. We send it to the model at temperature 0. Then we extract the raw content. Next, we validate the response using output guard. If validation succeeds, we return a structured dictionary. If the model returns invalid JSON or violates the schema, we catch the error and return a useful error payload. This ensures that the agent is always predictable and safe to use. Finally, we create a demo function. First, we define a concrete behavior spec for a requirement analyst agent. Then we create a behavioral agent using this spec. We print instructions, ask the user for a problem statement, and show a preview of the final shape prompt. Then we call agent.run and print the validated structured output. And last, we add the standard Python main guard, so the demo runs when we execute the file. And now we can run everything using Python main.py. We got an error that the application cannot find our OpenAI API key. Let's quickly fix that. For the purpose, we need to install one more module, .env. After it has installed successfully, we need to import from .env import load.env and actually invoke the method with override equals true. Override equals true ensures that this will override any existing environment variables with what you have specified in the .env file. Now let's try running main.py again. As you can see, the error was fixed. Now we need to paste any problem description and the behavioral shell will turn it into a constrained structured prompt. The output will always follow the schema unless the model breaks the rules, and if it does, the output guard will catch it. Let's now try it with a real prompt. For the purpose, we will use a short, vague prompt. Let's execute it. Once it has finished executing, we can see a short reasoning field, a clean, constraint-respecting answer, no hallucinations, no overreach, no architecture suggestions, and no code generation. This demonstrates the core idea. Specialization is engineered through structure, not through raw strings. Specialization isn't magic, it isn't personality, and it definitely isn't just a raw string. Specialization comes from structure. When you intentionally design the boundaries of an agent, when you enforce constraints that limit what it can and cannot do, and when you wrap the entire process in a behavior-driven architecture. You create a system that behaves the same way every time, under the same conditions. That is what gives an agent identity. That is what makes it reliable. And that is how you progress from a simple role-based prompts to engineered cognitive systems. This shift from loose prompting to deliberate behavioral engineering is the foundation of advanced multi-agent design. And if you want to go even further, the next step is extending this behavior shell with tools, so you can enforce tool-level constraints and capabilities as well. This is how you build agents that are not just smart, but also dependable. Subscribe to ByteBuilder and follow the series to keep building smarter AI systems together.